So I want to evaluate the Fourier series of f of x is equal to x, and x is between 0 and 2 pi. I already want to say that the result will be different if x is between negative pi and pi, as we will see later. And we will use the complex Fourier coefficients to evaluate our Fourier series, and at the end we will convert that into real Fourier coefficients. Okay. Yes. So I have the integral from so I have 1 over 2 pi times the integral from 0 to pi of x times e to the negative I n x dx. That is my complex Fourier coefficient. So n is an integer, of course, and the 0 from 2 to 2 pi is, of course, our period. And here we have our functions, and here we have our complex exponential, because we have deal with the complex Fourier series, complex Fourier coefficient, sorry. And so if we integrate that, so here we can do an integration by parts, and for that you can use the tabular method. Okay, the tabular method. You can look it up on the internet. It's a really nice way to do integration by parts. The tabular method. That's really efficient to evaluate Fourier series. I really recommend it to you. It saved me a lot of troubles in exams. And you are quicker and you do less errors. Really, look it up. So you evaluate this integral with the tabular method, and then you get this result here. And yes, now you evaluate it between 0 and 2 pi, and at the end you are left with I over n. Okay, if you rearrange a bit, okay, because here we have, if we insert x is equal to 2 pi, we get e to the minus I n 2 pi, which is always 1, and the 0 here, e to the 0 is also 1. So if we evaluate only this integral here, we get 0. Okay, we get 1 over n squared minus 1 over n squared, and so we get 0. And but here we have an x, so it's not the same thing. If we insert 0, we get just 0. So at the end you are only left with the thing with the 2 pi. So 2 pi times e to the minus I n 2 pi, so 1. This is 1 also. And you have negative I n in the denominator. So we are left with 2 pi over negative I n. And we have 1 over 2 pi in front, and you don't need to forget. So at the end you are left with I over n, okay? Now we need to be careful, because this, remember, this n is an integer, and here we always need to look at the case where this is not defined. So where is this result not defined? It is not defined if we divide by 0. So where do we divide by 0? We divide by 0 if n is equal to 0, simply. Okay, if we would have I over n plus 1, we would divide by 0 if n is equal to negative 1. Okay, but here that's not the case. Yes, so here we divide by 0 if n is equal to 0, so we need to evaluate this coefficient separately. So we evaluate c sub 0 instead of the general formula with n. And yes, so if you plug in n is equal to 0, this e to the minus I n x is simply 1, okay, e to the 0, so 1. So we are left with the integral of x simply. And if we evaluate that between 0 and 2 pi, and don't forget of our 1 over 2 pi, we get pi. So now we have found our complex Fourier coefficients using, as said, the tabular method for integration by parts. This is really a powerful method. Really look it up. I won't explain it in this video, but yeah, you derive a part of your integral and a part of the function inside your integral, and integrate the other one as usual, but it's just a lot cleaner and a lot better to deal with than the traditional integration by parts method. Really look it up if you don't know it. Yes, so now we can find our real Fourier coefficients. So we know that our an, so the coefficient in front of the cosine, is equal to cn plus c of negative n. So we just replace every n inside our final result with negative n. And so if we do that, we have cn, so I over n plus I over negative n. Okay, we replace the n with the negative n, and so that is simply 0, okay? So we get 0, which makes sense because this, we should get for this kind of functions, we should get 0 for the an. Under bn, so our function, is not our function is not even. It is like that, our function. If we have here the x and y axis, here is 0. This is an odd function, this x. So it makes sense that the even coefficients are 0. But as you will see, the odd coefficients are not 0, which makes sense because this function is odd, as said. To get our Pn, we do I times Cn minus C of negative n, okay? So you have our I, so our imaginary number, we have our Cn here as usual, but now we have negative C of negative n. So if we have negative C of negative n, we have simply In, okay? We have negative, negative, so positive. And so we get In plus In, okay? So we get 2In, okay? Here we have negative, negative, so we get positive. And so we get, we add both, and we get 2I over n. And don't forget this I in front of the whole thing. So if you multiply it, if you multiply both I, we get I squared, so negative 1. And so we get negative 2 over n. So that is our odd Fourier coefficients, real Fourier coefficients. And we don't need to forget a0, a sub 0, which is simply 2 times our c sub 0 that we got here. So we get 2 times pi. So we get 2 pi. This is 2 pi. And so our real Fourier series is simply equal to 1/2 of this a sub 0. So I mean, originally we don't even need to say that a0 is equal to 2c sub 0. We could simply say that a0 is equal to c0. That's just true, because here we multiply by 2, and then here we divide by 2. That's the same thing. I don't know why they do that way, but we needed to learn it that way. I don't know why, but yeah. Anyway, so we get 1/2 of a sub 0 plus the sum from n is equal to 1 to infinity of an cosine nx plus bn sine nx. And remember, our an is 0, so the whole thing with cosine disappears. And remember that this a sub 0 is simply the n for n is equal to 0, because sine of n is equal to 0. If n is equal to 0 inside the sine, we get 0, so there is no b sub 0, because sine of 0 is 0. But for the cosine, if we plug in n is equal to 0, we get cosine of 0, which is 1. And that's why we have this a0 here, okay? That we take it outside. That's why we begin by 1, because at 0 there is no pn, because sine of 0 is 0. And the a0 is simply if cosine of 0 is equal to 1, so we are simply left with a sub 0. Okay, that's why we begin at 1 and not 0. So I said our a sub n is 0, except for when n is equal to 0, where we get 2 pi. So if we take half of it, we get pi. And our Pn is this thing here, so negative 2 over n. And so we plug in this coefficient here. And we get pi, so or this part here, plus the sum from 1 to infinity of this Pn, so negative 2 over n times sine of nx. Yes, so that is our Fourier series. And now, as said at the beginning, the result is different if we integrate from negative pi to pi. This makes sense, but yeah. The result is different if you integrate it from negative pi to pi, so that your boundaries are not 0 to 2 pi, but negative pi to pi. At the end, you should get negative 2 times, it's the same thing, but you have this negative I to the nth power, so it is alternating. And that should make sense. I don't remember why, but it should make sense. Yes, it's maybe not that clear, but yeah, that's totally normal if we don't get the same result, because it's not the same domain, okay? Even if one could think that it's in both cases it's 2 pi periodic. Yes, I don't know why. Anyway, yes, so that was it. So really, to be quick and efficient, I advise you to use the complex Fourier series first, because it's a lot easier to integrate with e to the negative I n x. It's a lot easier to do an integration by parts with something exponential, so e to the something, than with cosine and sine. And also with cosine and sine, you need to do two separate integration by parts. Here you only need to do it once, and then you can find your real Fourier coefficients using the result. Yes, so it's a lot easier to deal with exponentials in integrations than with cosine and sine, and that's why the complex Fourier series are generally easier to deal with. And as for the integration by parts, I really advise you to use the tabular method. Look it up on the internet. That's what we did here. It's a lot easier and more efficient. Yes. And then you evaluate your integral, and you notice the case where you divide by 0 for the general case. Here, if you only have n in the denominator, so we only have the case n is equal to 0, but if it's, as said, something like, don't know, if at the end you get I over n plus 3, then you would need to consider the case where n is equal to negative 3, okay, because we have negative 3 plus 3, so 0. But here we only have the case for n is equal to 0. Yes. Yes, of course, in this case here, if n is equal to negative 3, you don't need to consider the case where n is equal to 0, okay, because you only get over 3, so not over 0. So you evaluate it separately, then you just plug in your n is equal to 0 or whatever poses problem, and then you find your real Fourier coefficients. So an is equal to c sub n plus c sub negative n, and bn is equal to I times c sub n minus c sub negative n. You do that, sorry. And then, yeah, you use your formula. So your a sub 0 is equal to 2 times c sub 0. And your formula at the end is f of x is equal to 1/2 a sub 0 plus the sum from n is equal to 1 to infinity of an cosine nx plus bn sine nx. Okay, I don't know why I put that here. Okay, and then you plug in your coefficients for an and bn and your a sub 0, and if one of those here is 0, then you just have 0, and that's it. Okay, yeah, so that's it. Thanks for watching.